These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There's a link to my website in the info box. The address is www.freelance-teacher.com/videos.htm. Or you can just use the link in the info box. Thank you. So titrations is really just an application of acids and bases. So people oftentimes have difficulty with titrations, but usually when people have difficulty with titrations is because they don't know how to do the basic acid-base reactions, because titration is just an application of acids and bases. So what is it that is difficult about acids and bases? Well, acids and bases are not intrinsically hard, but the problem is that there's many, many different cases. And each case is attacked similarly, but slightly differently. So students get all the different cases mixed up in their head, and they don't know which method goes with which other thing. So again, how many cases are there? Well, you could have a strong base with a strong base. You could have a strong base with a weak base. You could have a strong acid with a weak base. You can have a weak base and its weak conjugate. Also, you can have a strong, those are the different categories for that involve mixing two things together, for example. You could also have acids and bases on their own. A strong base by itself, a strong acid by itself, a weak acid by itself, a weak base by itself.
Yeah,
and
dissociate.
Yeah.
That's right. Well, of course, they always dissociate.
Yeah.
And if you have a titration, and then on top of that, there's polyprotic acids. Have you guys been covering those?
I'm also confused about those.
Yeah, so that makes even more cases, because you can have a diprotic acid, and the diprotic acid could be either strong or weak, and then that can be combined with a strong base, and then there's even a triprotic acid. Okay, so the first step to coming to grips with that is just realizing how many different cases there are. So here's the handout on that.
Thank you.
Thank you.
Sure. All right, well, this handout is not as much help as it might seem, or as we might hope, because all I've done is just list all the different cases here, because there isn't, to show how to do each one would take a couple pages or a couple minutes, so we have to go through the cases we need to learn here. But if you want to be prepared for all the different types of acid-base problems you might see, you have to understand how to work through all these cases. Okay, so every time you're doing a problem, you should ask, which case is this? You're learning how to do that case. So let's see, so if you look at the top of the handout, above the solid line or the thick line, those are the most basic cases, where you just have, you have just pure water, or a strong acid or a weak acid, or a strong base or weak base by itself, or a weak acid and its weak conjugate base. Those are the key cases. All right, then you can have underneath the thick line the situations where you combine two things. Now, the reason I put that thick line there is everything that's below the thick line is really two steps. First, you show how the acid and base react with each other, and then that's going to put you into one of the situations above the thick line. And then you're going to have to do another problem based on that. So anytime that you're combining those two things below the thick line, there's really going to be two sets of reactions. So the key is to understand these reactions above the thick line, because you're always going to end up having to use those. All right, and then down below, I just listed also the types of problems that involve polyprotic acids, and I put those in terms of titrations, because that's how that's often tested. Okay, well, let's dive in. Well, you guys mentioned titrations. I don't know, we're not going to have time to go through every single case here. Well, okay, so let's start with, let's work through this example. 100 milliliters of 0.1 molar hydrochloric titrated with 0.1 molar sodium hydroxide. We're going to draw the curve here. So what is our horizontal variable going to be for the titration curve?
Volume of base.
Yeah, it's the volume of the base that we're adding. So it would be in liters of sodium hydroxide. And what would be the vertical units?
Oh, would that be pH?
Yeah.
Yeah, sorry.
We want to see what's the effect on pH of adding different volumes of sodium hydroxide. Well, let's start with the Y-intercept. Let's try to figure out what the Y-intercept of this curve is going to be. That is, we want to know what point are we going to intersect the Y-axis.
Isn't it low because HCl is a strong acid?
Yeah, that's a good point.
Closer to 0.
Pardon?
It'd be closer to 0, like 1 or like
Yeah, we know it's going to be less than what?
the than 7.
That's right, we know it's gonna be less than 7. Okay, that's a good point. So if this is 7, we know we're gonna be somewhere around here. Let's figure out the exact number it's going to be. So let's try working that out on paper. Any idea how you would work that out?
When you do Ka, so you calculate the Ka concentration.
Okay, so let's try working that out on paper.
Yeah, that's
I don't remember how to do K.
Okay.
K. K of the reactive, products that are reactive.
Actually, it looks like we should go through that together, so let's do that. Okay, so the first thing we want to do for an acid-base problem is write down, what's the chemical reaction that's happening. So what is the chemical reaction that's going to be happening here?
HCl.
It'd be HCl
Yeah, that's
associates
good.
with water, so then it'd be H3O plus Cl minus.
You don't do HCl plus NaOH.
No, because right now you're just doing the dissociation of the HCl.
Remember that we were trying to figure out, I'm sorry, I interrupted you, you're saying the right thing, I think, yeah.
Oh, sorry.
So as you were saying, we're trying to figure out the Y-intercept. Well, the Y-intercept is when the volume of sodium hydroxide is 0. That is, we haven't added any sodium hydroxide yet, so it can't be reacting with the sodium hydroxide yet. Okay, so this is an acid, so it's going to donate to a proton to the water. So that would give us this chemical reaction.
Okay.
By the way, sometimes people abbreviate this just like this. As an abbreviation, sometimes people just pretend that this is just dissociated into a proton and chloride, but the way you wrote it was like this, and this is better because it's more realistic. The protons don't just float off by themselves, they're really being donated to the water. So you might see this done as a shortcut, but it's more realistic to write it this way, so maybe we'll stick with this. But either of these would give us the correct answer in this case. You could use either of these to get the correct answer, but we'll stick with the more realistic equation. Now we want to use a start-change end table. What amount of hydrochloric are we starting with? Well, we're starting with 0.1 molar. Start-change end tables will work for either moles or molarity, but it's more convenient here to work with molarity, so we'll work with molarity. So in this case, the volume doesn't make any difference so far. All right, and we're going to pretend that there was no hydronium produced at the beginning. Now we have to decide, is this a reaction that's going to go to completion, or is it going to go to equilibrium?
Because it's in a strong acid, it'll go to completion because strong acids completely dissociate.
That's right. So that's the key. That's well put. Any reaction that involves a strong acid or a strong base is going to go to completion. And any reaction that involves no strong acids or strong bases will go to equilibrium. Now, the water here is acting like a base, right? Because it's picking up the proton, and water is a weak base. But that doesn't matter because this is a strong acid. So they don't all have to be strong. You just have to have one strong acid or a strong base for the reaction to go to completion. Okay, what that means is when a reaction, there's two ways to solve problems. One is the equilibrium approach, and one is the limiting reagent approach. Well, when the reaction goes to completion, you use the limiting reagent approach. And when it goes to equilibrium, you use the equilibrium approach. So I think you were trying to use the equilibrium approach here because you were trying to use the Ka, right, which is an equilibrium constant. So that approach actually doesn't apply to strong acids and strong bases. In fact, you never learn the Kas for strong acids and strong bases because they don't really have equilibriums, right? They go to completion. Or if you did have the Ka, it would be huge. So you're just not working with it. We can approximate this as going to completion, not as going to equilibrium. This is what I meant when I said it's easy to get the different cases confused with each other. There are many cases where you do use Kas, but not for a strong acid or a strong base. Okay, so that's what we have to do to clear up those confusions. So the limiting reagent here obviously is the acid, because we're not going to run out of water. So we're going to use up all of the acid. So what's going to be the change in the hydronium?
Gonna gain
How much will it gain?
by 1 molar.
Yeah, because they have the same stoichiometric coefficients. So if we use up 1 mole of this, we make 1 mole of this. So that would give us 0 here and 0.1 molar here. What about the chloride? Well, chloride is neither acidic nor basic, so we don't need to pay any attention to the chloride. Anything that's the conjugate of a strong acid is not acidic or basic at all. That's what it means to be a strong acid. Something that's strong is something that has an unreactive conjugate, so we don't need to pay attention to the chloride in this reaction. After all, that's why this is not going to equilibrium. The forward reaction is going, but the reverse reaction is not going, because chloride is completely unreactive. So by definition, a strong acid or base has to have an unreactive conjugate base or conjugate acid.